Good morning and welcome to today's webcast, Reliability and Data Monitoring in the Age of Remote Working, sponsored by Kaeser Compressors. My name is Travis Hessman. I'm the Chief Editor of New Equipment Digest, and I'll be your moderator today. Before we begin, I'd just like to take a few minutes to explain how everyone out there can participate in today's presentation. First, if at any point the slides or audio seem to stop working, the best solution is to hit the F5 key on your keyboard to refresh the webinar console and resolve most common connection issues. Also, we do welcome your questions during today's event. In order to submit your questions to today's presenter, just type it into the Q&A window on the left side of your screen and then hit the Submit button. We'll be answering as many of those questions as possible during the Q&A session that'll follow the main presentation, so feel free to send those in whenever they occur to you throughout the presentation. And today's session is being recorded and will be available on the New Equipment Digest website within the next week for you to review. You'll be notified by email once that archive is available. Also, on your console, please note that the Kaeser logo is hot linked. If you'd like to visit their website during the webcast, you can just click on that logo and a new window will open. So it will not take you out of the webinar, which means you can continue to listen as you browse. And with that, I'd like to welcome today's presenter. As Engineering Manager, Neil Mehltretter is the key player in Kaeser's technical department, with responsibilities including product management, system design, and more. An authority on compressed air assessments, Neil's conducted and supervised thousands of industrial compressed air studies, helping users achieve significant energy savings and operational improvements. He has authored several nationally published articles on compressed air system optimization and is a frequent presenter on energy efficient system design. In addition to his bachelor's degree in chemical engineering from the University of Florida, Neil is an Air Master Plus certified, has completed the DOE Compressed Air Challenge 1 and 2, and is a certified energy manager. He is a KGI certified compressed air system specialist and is a master's certified system specialist through Kaeser's factory training program. All right, and with that, Neil, the floor is yours.
Great, thanks, Travis. Quite the introduction. So we've got a jam-packed session today, so thanks to everybody who's listening live, as well as those folks who are going to join us later on demand. This webinar is going to focus on compressed air reliability, identifying potential problem areas, what they are, and how to assess them. And then we'll move into data monitoring, how and what points to monitor, followed by trends and taking action. When we talk about reliability, we typically discuss buzzwords like uptime or lost productivity cost, but we don't necessarily talk about how well, or poorly for that matter, our plant systems are operating. For example, plant operators may not know system status and may need to actually visit the manufacturing floor to find out. That's like what we're seeing in this picture here. And this is typically the case for most compressed air systems, but that trend is changing, as we'll see later on. Let's consider, in this example, that plant pressure has actually dropped significantly. What could be the problem? In this scenario, we have to actually visit the compressor room or the manufacturing site to really figure out what's going on without looking at real-time data. So we're only reacting to the event versus being proactive. If we're data logging information or streaming information, then there's a chance we already know the problem before, or at least early enough to try to correct it. Same example as I used previously with a severe pressure drop in the plant, but here you can actually see that graphically. Pressure's fallen. And if you look a little bit closely, and like Travis said, I've looked at a lot of design audits, so this stuff is intuitive to me, but maybe not to you folks out there. But you can see there's actually about 5 different color of compressors that are running on this particular sample day. At the time the pressure drops, the pink compressor actually drops out, turns off for some particular reason we're not sure of here in the data. But that seems to be the particular reason why we do have a pressure drop, and then other compressors don't come online, and therefore we have the issue in the plant. So looking at the data, we already know what happened, and we can identify which compressor is the problem. Master controllers, like the graphic at the left, can provide further details on compressor operation in real time, which can be critical to plant operation. And since we're on the subject of reliability, let's have a look at typical failure scenarios within a compressed air system. Failures within a compressed air system can typically be separated into mechanical or electrical, and both can be affected by temperature regardless of whether the compressor is air-cooled or water-cooled. Temperature and pressure can also affect how support equipment such as dryers and filters actually operate, and that can make them less effective. The plant can also experience scrap or downtime due to compressed air equipment failure, low plant pressure, as well as air quality issues. Most mechanical equipment problems can be seen through increased wear, whereas with electrical problems it could be actually internal to the package or the compressor or dryer, what have you, or external to the compressor, dryer, what have you. And this could also be due to excessive wear. For example, rapid cycling of the compressor not only will result in increased valve cycling, but also cycling of your electrical components such as your motor or contactors, etc. Equipment failures can also be the result of your environment. Whether you have proper ventilation, either cooling air into the room or moving cooling air out of the room. Dusty or dirty environments also mean you should consider increasing your service intervals, like cleaning out your coolers more often or replacing dirty inlet filters more often. In that same vein, some areas of the country have high pollen content seasonally, so those types of maintenance intervals need to be changed according to the season. In addition, other areas of the country might be more susceptible to lightning strikes, so you need to plan for these occurrences up front. Likewise, if you have water-cooled units, you need to be aware of the water quality as well as flows, temperatures, and pressures. Lastly, improper operation, lack of maintenance, or the incorrect maintenance interval can lead to increased repairs or failures. So, how do you know if you're setting yourself up for a reliable system? We're going to walk through some best practices as it applies to your compressed air system. Specifically, what are the ambient conditions? Number one is good lighting. And really, it seems like a trivial thing, one that we take for granted. Good lighting is essential to be able to work quickly and safely in your compressor room. Number two is proper service access. Typically, if the compressed air equipment is installed as an afterthought, it's put in the hardest location in the plant to get to. And this can lead also to ventilation problems, as we're going to see in the next slide. And those ventilation problems can, complicate your service life. What we see here in these pictures, and obviously maybe flash is to do in the pictures, but the pictures to the left, dark, maybe a little bit of dirty environment, and then the pictures at the right show, brand new, clean compressor room, ample light, ample space around the packages. These are the things that we want to strive for. Clean indoor temperature-controlled environments, definitely what we want to look for. All your equipment has operating temperatures, maximums and minimums. So if your compressor room doesn't have minimum heating and the compressor's off, this can cause freezing issues within compressed air piping or even within the compressor. And again, dust and dirt can build up and affect compressor performance. So if there's a significant amount of dust and dirt in your environment, this is going to increase your service intervals. When I mentioned before typical compressor failures, temperature was at the top of the list. So ventilation, both cooling air inlet and cooling air discharge, are going to play a large role in how your compressor operates. If inlet louvers aren't large enough, you end up with a negative pressure in the room. So what happens is if you're trying to walk into the room, you're opening the door. If the door is a swing-out door towards you, as you open the door, you have a significant resistance, and air is just being whooshed past the door trying to get in. So that's difficult to do. So maybe that's your workout for the day. On the other side, if the door swings into the room, as you open the door, that door is going to swing quickly into the room, pretty much just like you have a high windy day when you're trying to open your car door and perhaps you're trying to keep your door from hitting the neighbor's car. So Negative pressure in the room is going to make your compressor work harder. So for the amount of flow that you're putting out, your compression ratio is going to be increased, which means your power consumption is going to be increased and you're taxing all your equipment more. Not to mention that you don't have enough cooling air, so your operating temperatures are going to continue to elevate and your compressor is going to shut down, which we want to avoid. Likewise, how we dispose of the waste heat from the compressor will also affect performance. What we see in the picture here at the bottom left is a compressor with a makeshift duct. Not recommended, especially something that's flammable. This is actually cardboard. However, the customer was trying to figure out if their compressor on the left, this was overheating constantly, but the compressor on the right was totally fine. So the suggestion was, hey, start pushing the air from the discharge away from the machine, and let's see if the compressor was actually inadvertently sucking in hot air, which it actually was. So thermostatically controlling your compressor room is highly recommended, and as you can see in the picture at the top right, this is the same compressor, just a front picture and a back picture. So you can see louvers are on the side of the compressor and also behind it. What you also see is a louver that's closed there on the left-hand side, and then the recirculating louvers on top of the compressor is actually open. So you're trying to maintain a balance within the compressor room. Lastly, consider everything that's in your room and how it can affect operating temperatures, whether it be non-compressed air equipment such as a boiler or other compressed air equipment such as a refrigerated dryer. Compressed air dryers also require a cooling air inlet and a means to remove that hot air. So exhaust fans would be required for these such dryers, as internal fans within the dryer don't typically have enough power to be ducted directly. Fans can also be used for compressors if ducting the compressor directly is not practical. The key is to maintain that room balance. All of your compressed air equipment requires maintenance. Yes, even your drains. And you can see from the picture at the top right, there's condensate that's building up on the concrete pad for the tank. All condensate should be disposed of properly according to local and municipal laws, hence the need for drains and a condensate management system. And what we can see from the picture is if this tank is actually a dry tank, meaning after all air treatment, we know there's an air quality issue within our compressed air. Maintenance on a recommended service interval for all of your compressed air equipment can help maintain reliability within your system, both from a compressed air equipment uptime perspective as well as an air quality perspective at the point of use. We talked a good deal so far, in general about air-cooled compressors, but compressors are also available water-cooled. And in many places in the world, or even in your particular facility, a water-cooled compressor can be a better choice than an air-cooled one, especially when it comes to heat recovery for processed water. It all depends on the application or the location of your equipment. Compressor operation is going to be dependent on inlet water temperature and inlet water pressure, as well as a differential between the inlet pressure and the discharge pressure on the package. Inlet water flow is a big deal as well, and also water quality. The first items have an immediate impact on reliability. If any of these inputs deviate substantially from what's required, you're going to see the compressor probably shut down very quickly. The pictures that you're seeing are actually a result of issues within the cooling water system for this particular plant. The compressor room actually flooded due to a water quality issue. So the cooling water was actually from a river, and fish actually got caught within the filter and grew and grew and grew until we couldn't have enough throughput through the filter. And then we had water that breached and got all over the facility. So obviously unexpected downtime there. Poor water quality can also foul your coolers and cause them to clog over time. Some coolers can be cleaned externally and some cannot. So be aware of that before you make your purchase and plan for a worst case scenario. Here's another example of a regular service maintenance requirement. It's not directly related to your compressor or your dryer or your filters, but it's within that cooling water circuit. So be aware of serviceable items for all of your compressed air support equipment and make sure that they're done on a regular schedule. Installing a differential pressure indicator on the filter, the water filter, could provide early maintenance indication and therefore is highly recommended. Okay, so what do you see? Another great opportunity for us, when it comes to your compressor room, frequent visits definitely help. We're talking about data monitoring here, not going to the compressor room, but seeing what's going on, maybe using a camera remotely, that's going to help. When something's out of the ordinary, you want to evaluate. Look for heavy dust and debris. Are your coolers clogged? Is there water or condensate visible on the floor, which is what we're seeing here in these pictures. In the picture at the left, we see what looks like water on the floor in front of the compressor. It's a clear liquid, so probably not condensate, but where is it coming from? Is there an area that's not sealed off from the environment? Are we getting some driving rain into the room? So what we did find in this particular situation was a seal issue at the roof line, and rain was getting into the compressor room. Thankfully, we caught it early enough, and there was no damage to the equipment. The picture at the bottom right, going counterclockwise, shows where oil-absorbent pigs and pads have been used underneath the compressor. So, we want to follow up, figure out why this was required. Is this a maintenance issue? Is this something else? The picture at the top right, if you look closely, you'll see plastic, a little bit of plastic on the top right, which is the electrical cabinet for this variable frequency drive compressor. What was happening, if you see the ducts coming off both of those two compressors, those ducts were not sealed at the roof line, so when we were having heavy rain, we were getting water ingressing into the compressor room and then on top of the compressor, and unfortunately for that variable frequency drive, water also got into the control cabinet and the compressor was damaged and it was down. That's really the big issue is not only you have a serviceable item and now you have a high charge to replace that item, but you also have downtime for your facility. So sealing the roof line is a really easy and inexpensive thing to do. Replacing the drive, bringing in a rental compressor, having production downtime, not something you really want to have on your plate. Changing a little bit, talking a little bit more about the 5 senses when you walk into a compressor room, those are important too. How do you feel? Is it warm? Is it cold? What's going on? Elevated temperatures, like we've talked about already, can indicate pending service issues. The picture at the left actually shows compressor bank on the left-hand side of the room, and then on the right-hand side, further back, are refrigerated dryers. When you look at the camera the picture from the FLIR camera, you'll see that it's 127 degrees towards the refrigerated dryers. That's a very hot area for the dryers, and it's going to be hard for the dryers to cool the compressed air, which means that you're probably going to start to get air quality or moisture-related issues downstream. Further on the right-hand side, hard to see maybe in this graphic, but looks like the coolers might be plugged, dusty, dirty, and you can see maybe elevated temperatures using the FLIR camera. So, again, walking into the room, you're going to see some things that maybe you won't be able to see with the naked eye, or feel some things that you won't be able to feel, obviously, from far away. As a summary, for a reliable system in the compressor room, you want to actually look for undersized or oversized compressors. That may be part of your problem, that it's cycling too much, or you don't have enough air, so pressure is dropping. Without redundancy for compressors, dryers, or filters, you may be inadvertently causing productive downtime. Other things to look for would be undersized piping or storage, or undersized storage, and these conditions can cause the type of failures that we were just discussing. In the plant, if you're seeing a high scrap rate and production downtime, this could be caused by deficiencies in your compressor room as well. Production is also susceptible to pressure and air quality issues, and many systems also suffer from undersized distribution and or point-of-use piping. As well, many systems can benefit from point-of-use storage. Now that we've covered some of the key points regarding compressed air reliability, let's translate that into what you could actually monitor to help improve your reliability and trend your compressed air system. Taking a look at some of these key features of smart factories and smart machines, I'd like to highlight two in particular. Number one would be reduce maintenance costs, and number two is actually increase uptime. Again, uptime is essential for lean manufacturing companies. Any downtime can bring your entire production to a halt. Looking at three different maintenance models, in the past we've been reactive, run to repair, run to failure, and it's fair to say that strategy is fairly common today. There are plenty of other strategies out there, specifically moving towards that preventative maintenance. Typically preventative maintenance intervals, oils, filter changes, etc. The future is predictive maintenance. Trends are created by analyzing data. Maintenance is going to be planned in time and before equipment shutdown occurs. So think of it as maintenance only when needed. No doubt there's a huge benefit for working towards predictive maintenance. And here are some key benefits. From a customer perspective, we're reducing asset lifecycle cost as well as energy cost, increasing that uptime again, and improving system performance. From a service provider standpoint, this can improve just-in-time inventory and allow for diagnostic and troubleshooting from afar, which is great. From a supplier standpoint or manufacturer standpoint, this information can be used in product redesign as well as improving part availability, like kind of we saw also with the service provider standpoint. Change is not without its challenges, and these challenges are going to differ for each of the groups that we're discussing. From a customer standpoint, investment must be made in these smart machines. So it's probably going to be a little bit more expensive, or you're going to have a little bit more overhead to get that information. The other thing, the big thing really is, often IT security is the big concern regarding sharing information with any outside parties. From a service provider standpoint, some technicians are extraordinary when in front of equipment, but translating those skills into data monitoring, or vice versa, taking data monitoring skills and giving it to a technician, those can be difficult. For suppliers, how to integrate that information into R&D, applying new hardware and software to get the connectivity needed at a cost that fits the market. And then, shifting our focus to analytics and security of what's coming in. So, yeah, there's definitely a lot of challenges and certainly a lot of benefits for all parties. Let's take a look at some of the data basics that need to be implemented. In the next steps, we're going to take a look at how to structure an IoT cockpit and avoid data overload. As well, we're going to trend analysis and talk about predictive maintenance, how to differentiate between data that's critical to your operation and what data is important to gather but doesn't necessarily have to be collected as frequently. So we'll call that non-critical data. Some very key terms there. Let's start with critical data. Temperature. At the top of our list already, temperature is a critical value within your compressed air system, and there's multiple different points. Oil temperature, a good indicator for compressor cooling flow. Running over consistently high temperatures can reduce the lifetime of the unit. Something's wrong with the unit, and maintenance is going to be required if you're seeing high oil temperatures. Air and discharge temperature is another critical data point. Higher inlet temperature is actually going to significantly increase moisture content and can overwhelm dryers and in return lead to a premature dryer failure. Worst case scenario, required air quality can't be maintained at these elevated temperatures and could lead to loss of production, which obviously we want to avoid. Other critical information, motor temperature, similar to oil temperature, good indication of loss of cooling flow, but it's in particular across the motor. Overloading the motor will increase the motor temperature. So Pressure, also besides temperature, is another critical value. So we're talking about line pressure or downstream pressure, and that could also be discharge pressure from the compressor, compared to an elevated internal pressure could be a sign of a restriction at the discharge of the compressor or internally. Maybe you have an issue with the oil separator, or maybe there's an issue with your minimum pressure check valve or something like that. Increased differential pressure for your oil is also something to be cognizant of, as well as inlet filters. So a good gauge if there's clogged or contaminated filters. Furthermore, a permanent replacement due to higher ambient contamination. So things that you want to be looking at. Alarms, a big thing that you want to be getting alarms from your system. Typically shutdown for the compressor, or even preventing the compressor to run. This highlights that alarm requirements or alarms require immediate action, and it's a good practice to set up alarm notifications pushed down to your mobile device, emails, text messages, etc. Air consumption in compressed air systems is another very important value. So customer demands downstream can help identify leaks and artificial demands during non-productive times. You can also use this as a basis for future needs. So I'm going to expand this particular line, and I need to know what this other line's doing. And it can improve your production process overall. Non-critical information, such as compressor-specific power or station-specific power, and so those are power consumed divided by the free air delivery provided. So think of it as power versus flow. That's a benchmark on how efficient your station is actually operating. Decreases in specific power or an increase in power consumption for no change in flow could be the result of inlet restrictions to the compressor. Controlling a station based on specific power can actually result in higher energy savings, but that equates to a higher level master controller as well. Load energy ratio considers total idle energy compared to load energy. So compressors are most efficient when they're fully loaded or they're off, and typically you want to see a high number for your load energy ratio. Other non-critical items, compressor utilization, in particular for multi-compressor stations with same-size equipment. The run hours offset a feedback for how well each individual compressor is utilized by a higher level controller. The idea is that we're trying to balance service hours with like-sized compressors so that they are all due for maintenance at the same time, rather than having your service provider make separate trips with higher costs. And last but not least is compressor cycle time. Also, you could talk about this as duty cycle. Frequent compressor cycling will result in increased wear and tear, and therefore is a good indication how well or how poorly a system is designed. Let's go through what seems like a relatively simple example. Here we have a single variable frequency drive compressor. It may be hard to see, but from bottom to top, actually at the bottom we have a gray line. That's the load status, so when the compressor is loaded, making air or off. We have inlet temperature in the darker orange, and then we have motor RPM in what looks like maybe light yellow or light orange. Motor RPM for a VFD can actually correlate to flow, or what we were talking about before, air consumption. And air and discharge temperature is the blue at the top. What we're seeing here in this example is, as flow increases, operating temperature significantly increases. Ideal operating temperature for oil-flooded rotary screw compressor should be in the 180, 185 degree temperature range. And what we're seeing is actually a very low operating temperature to start with there at the left-hand side, and then a very high operating temperature, which actually gets above 200 degrees Fahrenheit once production starts. The inlet temperature also increases to almost 110 degrees Fahrenheit, so it must be a hot day, or maybe we're not able to remove some of that air. Remember we talked about ventilation? And then this actually all occurs right before the compressor shuts down. So, here we're only looking at, a little bit of time, but if we're seeing this kind of trend happen multiple days, weeks, and so on, then we know we've got some issues that we need to deal with. We've thrown in quite a bit of information here on this particular chart for a 55 kilowatt variable frequency drive. So we've got temperatures, pressures, and flow. Again, that flow is by way of RPM for the motor. And temperatures here are within expected ranges. No issues to report for this particular 1 hour snippet. So here everything looks good. But same compressor during a low demand period. And we're only plotting motor speed. Again, we're talking motor speed as air consumption. We can translate that. Versus inlet temperature, air and discharge temperature as well. Notice that the temperature is significantly lower for that air and discharge temperature than that 185 degree Fahrenheit target that we talked about. And this type of low temperature can lead to air-end failure, which we obviously want to avoid. So something that we would need to really look at for those off-peak periods on how we can handle this a little bit better. Switching gears a little bit, over time you can also trend air quality. Most facilities would consider pressure dew point the staple of an air quality measurement. After all, moisture in your production line could result in plant stoppage and potentially millions of dollars worth of product scrap. Dew point monitors are available off the shelf and can be added to any compressed air station, either to be sent as a 4 to 20 milliamp signal to your plant control system or via a master controller. Alarms and warnings can then be set to ensure that the plant addresses any issues that arise. Particulate and oil measurements are more difficult, but there are devices out there which can help provide trend data. Be careful, as in order to get the kind of resolution, high-quality devices need to be used for particulates, which are expensive to install. Very expensive, like tens of thousands of dollars. For oil concentration, sampling can be done periodically and evaluated, then sent away to a third-party representative. Other things to look at, lubrication analysis, as well as vibration analysis. Measuring your cooling water data, like we talked about earlier, those can give you some additional monitoring points to help better manage your compressed air station. So it's the critical information that we just talked about and the non-critical. These things mentioned here on the slide, maybe they're critical to you. Trend analysis is the basis for predicting future events. Now, these charts that we're showing right here is a simple overview. I'd like to highlight two of these particular values. Number one, estimating the future maintenance date based on current and historical data. So, that's one thing we want to do from the trend analysis. And then number two, compressor utilization based on status information. Reliable trends can't be based on just a few data points. Like we saw in our two VAV examples, this requires a pool of real data. Next, we take a look at some of the challenges that we face today. A lot of high-level IT security systems are in place, which, don't get me wrong, is a very good thing, but it could be contrary, it could be challenging, actually, to implement simple IoT solutions within current IT architecture. Another challenge is limited signal strength and upload bandwidth at remote locations while implementing an IoT solution via a cellular network. Over the years, we've experienced actually a decrease in cost per bandwidth, which is definitely a good thing. A decreased cost for data storage on the cloud, and then we've seen the implementation of algorithms that sort through data. So now, does that mean we can stream every single point, as much data as we want? Well, too much data leads to what we call data overload, and actually can be a distraction. So, more data isn't always better. How do you avoid data overload? It's important to have a basic understanding of your asset. Categorize critical and non-critical data points, as we discussed a few minutes ago. Implementing a good troubleshooting guidelines, a great point here, and not always isolating each value or data point, but looking them at as a whole, from a synergy standpoint. Troubleshooting guidelines, define the problem, collect information related to that problem, then analyze the data to find the root cause, and then determine if the information is sufficient to propose a solution, and if so, test and implement that solution. Let's talk a little bit about data intervals. I mentioned this a little bit before as well, but data can update per millisecond, and that's not most likely what you require, and it actually could be contrary to mission-critical data and applications. Seconds to minutes worth of data updates, that's sufficient for compressor-critical data. Minutes to hour updates would be sufficient for compressor non-critical data. Now, next, we're going to take a look at examples from an IoT cockpit. IoT cockpits are not limited to a web browser. Rather, it should be accessible via a mobile app with push notifications, text, or email. It's a good practice to have a geomap for different locations. So if you're an energy manager, you have multiple plants, you may want to be looking at something like the top right. Station health status based on color coding. So, alarm would be in red, orange is maintenance due, green is health status fine, gray here means that we've lost communication. So, health status, boom, now I've got a macroscopic view on what's going on. Group critical data together in one overview, like we're seeing at the top left. Line discharge pressure, oil discharge temperature, motor winding temperature. Those are things that might be critical, and you want to have a look as soon as you open the cockpit. Display important compressor status information such as load, idle, or off. So what we're seeing in the bottom left screen, those are equipment numbers on the y-axis, and then we've got time on the x. And we can see when compressors are actually loaded, which is the solid green line, or idling, which would be a small little bar, or off. So we got a good indication on what's going on. And then list all current messages. So we see on the right-hand side, those are all color-coded. So, alarms, one color, warnings are one color, just communication messages might be another. So we're going to stop here and talk a little bit about the two types of controllers that you might find in a compressed air system. One is the individual controller for the compressor, and then the other would be a master controller that would bring multiple controllers together, and maybe even additional devices like dryers and filters and so on. To give it an example, an individual controller is like a pilot in an airplane. Takes care of things while you're up in the air, while the control tower is going to monitor and provide guidance and direction to multiple planes. So that's more like your master controller. The individual or compressor control provides safe local operation by monitoring and controlling all relevant signals and components of the compressor or dryer and so on. Most modern compressor controllers, they're going to keep track of maintenance information either by hours or temperatures or differential pressures and cycles. And they typically also keep historical records with date and timestamps, which is great. Depending on the compressor type, there also may be various options on how to control the compressor, like a start-stop or a load-unload, or maybe the compressor is equipped with a variable frequency drive or variable displacement or modulation control. These controllers are using discharge pressure as the basis for the control action. So master controllers or system controllers come into play if you're dealing typically with two or more compressors in a system. And one key aspect is the monitoring of the entire station, or even the entire compressed air system, so not just the compressors, but dryers, filters, valves, as well as additional sensors, maybe even pressure dew point, or water inlet temperature, or water flow, and so on. So master controllers can take that information in as well. Compressed air systems are quite often integrated to higher level controls or industrial automation systems or building automation systems. Industrial gateway enables the compressor to communicate via industrial protocol, and that can be the basis for IoT solutions. Nowadays, there are quite a number of IoT gateways available, such as Ethernet IP or Modbus, just to name some common industrial protocols. So these are things that will allow you to communicate directly with your station. Here we're going to look at a simple, low-cost example on how to implement an IoT architecture. Very generic overview, sufficient if you're interested in a limited amount of data points. So Modbus TCP, simple free protocol. A lot of low-cost software is available, or even freeware that supports Modbus protocols. Low-cost IoT or IoT gateways that communicate to Modbus TCP. So single-board microprocessor, such as a Raspberry Pi with supported Wi-Fi or LAN connectivity. Building a secure channel, example would be MQTT. It's a lightweight messaging protocol. Low-cost cloud database and API for subscribing and publishing data to. And at the end, you've got end user, desktop or mobile app to display those data points, like we talked about with the IoT cockpit. Now we're looking at an example collecting more data. So not just from a compressor, but higher level controller, master controller, or even building automation system, certainly more appropriate for larger amounts of data or bigger systems. Most common higher level controllers, master controllers, they're going to have onboard storage or even use storage in a cloud. Modern air producers, compressors, typically support industrial Ethernet, which simplifies that data collection. That collected data then can be pushed via a secure network to a cloud or data server, and the IoT cockpit then can be subscribed to that cloud or server to receive real-time data. Good IoT cockpits allow users to, number one, build individual charts or graphs, subscribe to different data points for different applications. So, maybe a technician's dialing, maybe product monitoring is dialing in, maybe the customer's dialing in. And then also to be able to create reports. And that's just, a few of the options you might have. Now that we've talked about monitoring options and building an IoT cockpit, here's an example of how these could look. And we discussed generally how it could be done from a customer level. And it requires a bit of integration on the customer's end and provide some key metrics as well as alarm functionality. If you choose, there's third-party providers out there that could monitor the information for you or set up your cockpit. And finally, there's compressed air service providers out there that can provide some level of support as well as include predictive maintenance algorithms. So these are things that you should be considering when evaluating your data monitoring options. Probably one of my favorite slides, but I'm a data guy, so that's kind of where I live. This shows you some graphs that you can have at your fingertips. The slides on the left show you operating condition for the compressors at the top. So those are those green lines up and down, and then also shows you how the operating pressure is going. So just a simple instantaneous status. Is everything good? The graphic on the bottom, on the left, shows you operation over time. So it's an energy cost table. You can change the day or the month or the week and see how well your system's running. So it give you a utilization on your compressors, load kilowatt versus idle kilowatt. Again, we want that to be as close to 100% loaded as we possibly can. Also can look at your specific power versus flow. They're highlighted at the bottom. So these are things you can get in real time. The other things, everything's running fine, you haven't heard anything. Maybe you get, on the right-hand side, you maybe just get emails. You get a maintenance report as you're getting closer and closer to that maintenance interval. So now you and the service provider know, okay, these are the things that need to be done the next time. And instead of the service provider calling you and saying, hey, what are the hours on your unit? The service provider is calling you and saying, hey, it's time for your service in 2 weeks. This is what we're going to do. This is what's due, et cetera, et cetera. And then you can also get an energy report monthly on how your compressors are actually operating. So, really powerful stuff that's out there today. When you're considering how to integrate your compressed air station, with a third party, there are many different options. Preferred option tends to be cellular. Here's one way that a master controller or an individual controller could actually be monitored. Just a word of caution, be sure that the cellular coverage in your area is good. So here's a map of one particular provider. Looks okay in the upper Midwest, maybe really just Michigan, Chicago area, and on the eastern seaboard, but really in the middle of the country, not great. And then also decide whether or not you want cameras to be a part of the process or not. Cameras can provide even further resolution as to what's going on in your compressed air systems. Cameras with motion sensors can trigger email alerts as well as when the compressor room is actually entered. And if you desire such resolution, it can actually take pictures or stream video. And it can also give your technician some idea about how the system's operating from a remote perch. So, can be a really good addition to whatever it is you're doing out there. We looked at some data earlier, and that was for an individual compressor or compressors, but that can also be macroscopic for the entire station. Certainly if you get an alarm message to your email or your phone or both, you want to know what's going on. Being able to dial in as an owner or a service provider can be very helpful from troubleshooting system problems. And as we see here, the graphic on the left, there's actually an alarm for one of the compressors, and that compressor goes down, and for a time, pressure is severely low. Also, all the compressors seem to shut down later in the day, and that's probably most likely from somebody who's visiting the system, and maybe to try to figure out what's going on, they shut the whole thing down. This kind of information is great to have at your fingertips, but again, in that particular case, we'd be reacting to the system. So here's an example for predicting future consumption, flow consumption, as well as temperature trends, and then detecting abnormalities based on algorithms via an IoT architecture. So this can enable operators or third parties to schedule customer-specific maintenance visits. Therefore, we can say that algorithms are a substantial help to sort through pools of data. They simulate different scenarios based on a digital twin of the existing system that's there, and they can piece together the right trends and predict future events, which is very powerful. So don't shy away from this type of analysis, but keep in mind that operating conditions in the compressor room will have a direct effect on the reliability of your compressors and compressed air equipment. Applying the recommendations we've discussed will ensure that your system is reliable and efficient. So, ventilation, ambient conditions within your room, performing the maintenance, or actually knowing what the maintenance is. Is it severe duty or is it regular duty? What maintenance schedule do you need? Don't forget about your cooling water system or your sub-supply systems to your compressed air station. Visit the room regularly, or if you have a camera, you can check in. And then designing flexibility to your compressed air system, as this is going to help ensure your compressors are properly applied and therefore reliable. There's a multitude of data points that you can collect to better monitor and manage your compressed air system to help improve reliability, increase uptime, as well as reduce maintenance cost and increase your energy efficiency. Man, there's a lot. Understanding what points are critical to your operation and which are highly useful but not so critical, that's a big step in effectively monitoring, tracking, and analyzing your compressed air system data. And avoid that data overload. Take a look at your current system. What are the possibilities? What are the requirements? What are the obstacles? What are the next steps for your plant, and how do you get ready? The hint that we'd like to give is look at the communication capabilities and the equipment you already own. and start using it. While some advanced IoT capabilities present challenges, there are simple ways to proactively improve your plant's performance with today's technology. A comprehensive leak detection program, regularly scheduled lubrication analysis, and effective air quality components in your compressed air system will have a big impact on your system's operation. We see real improvements in life cycle cost reduction as well as asset management in those plants who employ proactive techniques. So I'd like to thank all of you for joining us today, and I believe now we have some time for questions. So Travis, back to you.
Well, thank you very much, Neil. That was brilliant all the way through. You weren't kidding. That was jam packed with a lot of really fantastic information. And we are going to jump into the Q&A now to try to wring some more insight out of your brain. That's all right. So we already have some questions in, so we're gonna hit those. We have some time if anyone else has some burning questions you want to get in. And while Neil is answering the question, we ask everyone out there just to take a minute to complete the feedback form that appears on the left side of your screen. All right, so the first question here looks like it deals with trend analysis. How long do you recommend collecting data before you get into trend analysis?
Yeah, it's a great question. You know, we talked about data overload, and you want to avoid that. You know, I would recommend, number one, you want to figure out what it is that you're looking at first. So, you know, typically speaking, at least a month's worth of data is definitely important. You know, especially if you're changing things in the plant, you know, you're adding equipment or you're changing production equipment, you know, the trend analysis can look very different. You know, so I definitely recommend, you know, starting at least with a month's worth of data. You know, when we're doing some of our system design audits, we're typically looking at 2 weeks worth of data, and then we're extrapolating for an entire year. You know, so you know, some folks want to play it, you know, cautiously, and we're going to monitor this for multiple months. You know, so I'd say, you know, baseline would be, you know, a month worth of data, and then see kind of what you have, what your trends are. Maybe not make any really specific moves, but, you know, okay, these are the things that we've noticed are maybe outliers. Let's start to prepare for those things, and then what happens next month. And, you know, as you get more and more data, then now you have a better understanding of which direction you want to take the system.
Excellent. Thank you. All right. Another question came in here. I use food-grade lubricant in our equipment. Should I check it more frequently?
Sure. You know, that's a great question. You know, food-grade lubricant is going to have specific service requirements to begin with. You know, I would check with whatever supplier you're getting your lubricant from as to what the recommendations are. You know, but typically, general lubricants and food grade are typically 3 to 4,000 hours of operation. So, you know, whereas synthetics are maybe a little bit longer. So, you know, typically, you know, like we mentioned earlier, what's going on in the compressed air system may dictate, you know, whatever the recommendation from the manufacturer. So if it's 3 to 4,000 hours. I'm stuck on months here. Sorry, Travis. You know, if that's what it is for general service, then and you have a general service application, that might be fine. But if you're in a severe service with, you know, dusty, dirty environment, elevated operating temperatures for your system, then you're going to want to probably replace that lubricant more often. Oil analysis can also help with that. So, you know, you want to take that oil sample maybe halfway point between the 3,000 and see where you're at. And then you can figure out for your system what's best.
Got it. Excellent. And here's another one. It's a question that comes up all the time in our normal coverage, and I think it goes back to your data overload points. And it's a key one. What is the most important data point that people should be looking at?
Well, I think I've mentioned this the most, and I'd say operating temperature is probably the key. And every system is going to be a little bit different. So, for your system, operating temperature might not be that key. It might be pressure, it might be flow, it might be air quality. Typically, if you're looking at operating pressure for the individual compressor, you'll get a very good indication on, if you're in a severe service application, you're at elevated temperatures, you have a ventilation issue, it can really open your eyes to what's going on. It could also give you an indication on whether you're undersized for the system or oversized for the system. So those are things that, I'd say are pretty important. It's always difficult to choose, it's like choosing a favorite child. I love them all, and I'll only tell my wife which one is my favorite. So.
Oh, well, good. All right, we have another question here, and it's fantastic. It's probably the question of this whole era. It's which department should lead the transformation project from manual to automation, smart factory, et cetera? Should that be IT, quality, operations, production? Where does this sit?
Yeah, this is a hard one to bring up because, typically in every organization you have groups that work very well independently but may not work well together. So what you really need is buy-in from upper management that this movement is important and it's the wave of the future. So if you have buy-in from upper management, say your general manager or plant manager, let's say if we're talking plant level, then they're the best ones to help you shepherd the movement. But like was mentioned in the question, there are so many groups that are required that if you don't have the support from upper management, getting the buy-in from all the other groups may be difficult. So, my opinion is typically, from a plant operations standpoint, those are the folks that will benefit the most from having the data. But, from a quality standpoint, if we're talking, air quality or pressures and flows, those might be very important. IT, you can't leave those folks out. They know so much about, how your system is set up, how your network's set up, what works and what doesn't. So you have to obviously involve them as well. So, in the end, it's more of like a root cause analysis. You want to bring in every player that has an opportunity to provide some insight to it, and you want to get feedback and buy-in from management. But from my perspective, kind of the leader would be either operations or engineering because that's more so what they know. Reliability engineers and so on, or your if you have an energy engineer in your facility, those are the kind of people that probably would be the leaders. But you got to bring everybody in.
Perfect. All right. Well, thank you very much. And it looks like that's taken us right up to the top of the hour, so we have officially run out of time here. So I'd like to thank Neil Mehltretter and our sponsor, Kaeser Compressors, and of course everyone out there for tuning in today. As a reminder, if you did register as a group, we ask that you add the names and emails of everyone in attendance onto the exit survey. And with that, on behalf of New Equipment Digest, we wish you a productive remainder of your day. Thanks a lot.